Greetings to all and welcome to this lecture. We are in module 4, lecture number 5, General Analysis 2. So, in previous lecture, we started analyzing the 3-terminal MOS structure, which we said that to provide an additional connection to this inversion layer, we have added a third terminal which we called it as C, and this voltage is VCB. So, in the basic 2-terminal structure, we have added another terminal VCB, and we said that this VCB plays an important role when the electrons will come at the surface, meaning the inversion electrons will come at the surface. So, in previous lecture, we have seen how these equations what we have derived in 2-terminal MOS holds good by replacing N naught by N naught e to the power of minus VCB by phi t, or 2 phi f, which is surface potential, by 2 phi f plus VCB. So, in previous lecture, we have also discussed that the impact of VCB is not visible when the device operates in accumulation or depletion. So, either it is in depletion or in accumulation, the impact of VCB is not visible because you do not have inversion layer near the surface. So, let us explore what will happen when the device will be in inversion. It means you increase VGB in such a way that your device enters into the inversion. We will also see how the other quantities like the channel charge, QC dash, inversion charge, capacitance, surface potential, all these quantities of 3-terminal MOS, how it get affected with VCB. So, these are the learning outcomes of this lecture, which will help us to analyze the 3-terminal MOS in great detail about inversion, accumulation and depletion. Let us do a quick recap. We started analyzing the 3-terminal structure where we said that instead of having only 2 terminal, which is gate and body, we added another terminal which is C. C stands for contact here, and we connected VCB and saw that the impact of VCB is coming into picture when the inversion layer come near the surface. So, we have explained this impact by using energy band diagram. So, this energy band diagram is plotted for deep in bulk, which is p-type body. When you apply the positive gate voltage, then the bending starts, and if the bending increases and EI, which is EI bulk here, goes below the Fermi level, then we said that the inversion starts. So, for the inversion, the surface potential should be 2 phi f, where phi f is nothing but Fermi potential given by kT over q log of Na by Ni. So, if you have a 2-terminal MOS structure, this is gate, this is oxide and this is p-type body. If I make a band diagram, so the p-type band diagram will look like this, where you have a conduction band, valence band, intrinsic level, and this is Fermi level. When you apply a positive voltage at the gate, this positive voltage will cause a bending, and hence EI bends, and at some extent it will touch EF. At that point, we said that this is depletion. Beyond that value, if you increase VGB, it means this is VGB. The bending continues, and at one point of time, this EI, which is called as EI surface, goes below to this Fermi level, and hence the total bending is phi f plus phi f. That is all about 2-terminal MOS cap. But what will happen if you apply a third terminal here and apply a VCB in this third terminal? The moment you apply VCB, this VCB causes a shift in the Fermi level. So, you have electron here in n plus region, and this VCB causes a reverse bias junction because you are making it positive. In the reverse bias junction, when you plot an energy band diagram, then you will see that in the surface your Fermi level is different than deep in the body. In deep in the body, your Fermi level is EFP, and in the surface it is EFN. So, the difference is given by Q times of VCB. So, the applied voltage between C and B is nothing but the split into the Fermi levels, and these Fermi levels are called quasi Fermi level. Now, if you want to measure the total bending, that total bending, let us say this is EC and this is EI, right. So, the total bending should be in such a way that the surface potential should compete the rise in VCB, and hence the total bending can be written as the total electron concentration at the surface can be written as N naught e to the power of EI bulk minus EI surface into e to the power of EFN minus EFP divided by KT, here also divided by KT. This is the total surface potential, and this is the quantity which is nothing but e to the power of minus VCB divided by phi t. That is what we started our analysis, that wherever the VCB is coming into picture, this actually influences the surface charge, which is inversion charge, and hence we can use the analysis what we have done for 2 terminal MOS similar as for 3 terminal, except you can replace N naught by N naught into e to the power of minus VCB by phi t. Later we saw that because of this VCB, the surface potential increases. It means increase in VCB is actually reduces your inversion charge, and hence to get the same amount of inversion you need to increase the VGB in such a way that surface potential increases and hence the inversion starts. That amount of increase is can be reported here, meaning the surface potential influenced by VCB is can be given by 2 phi f plus VCB. When you increase VCB, ultimately it will kill your electrons, the surface electrons, and hence the depletion starts. So, this charge line is denoted by depletion charge. So, this is given by QB dash, and hence you see the charge is not affected because of VCB. You have to increase the surface potential to get the same amount of inversion, and that is what we have already discussed, that VCB will not influence the depletion region. Similarly, the VCB will not influence the accumulation region, because in accumulation region near the surface you have holes, and the influence of VCB through this N plus layer on hole is not there. So, by considering all these charge analysis, we derived a closed form equation of charge considering VCB. We found that the VCB is not coming in the hole contribution term, VCB is not coming in the dopant ion contribution term. Instead, it is coming only when we are talking about the surface electrons. So, we need to take utmost care when we are making 3 terminal MOS cap and connecting the inversion layer through external world. By this we derive a QC dash for different region of operation, like in accumulation and depletion, and we found that in accumulation it was given as signum psi s, which is psi s is negative. So, signum will be negative, negative and negative positive. So, QC dash for accumulation can be given as 2 into Q into Na into epsilon s into phi t e to the power of minus psi s by 2 phi t. That is what exponential dependency, and there is no term of VCB coming in accumulation. Similarly, when we talk about depletion, we can simply say only we need to consider the dopant ion contribution. Because of that, QB dash can be given as minus of 2 into Q into Na into epsilon s into root psi s, which is similar as here. So if you plot QB dash with respect to psi s, ultimately you will get this equation, and hence here also VCB is not coming into picture. But when you include the electron contribution, then VCB will come into picture, and the surface potential is also fighting against 2 phi f plus VCB. Further, we derived a closed form equation because we are interested what is the surface potential and the channel charge with respect to the applied gate to body voltage. Here also, if you see carefully, that VCB term is coming here when you are discussing about or including the electron contribution term. So in today's lecture, let's go further and see what will happen when we'll talk about the inversion. So in inversion, again we know when in two terminal structure, you need to increase the VGB in such a way that surface potential should cross 2 phi f. In general, for inversion, it should be 2 phi f plus phi z0. However, when it is all about 3 terminal, you need to increase the surface potential with reference to VCB. So here this is VCB, this is N plus, here this is oxide and gate, this is body, and this is VGB. So what will happen when you increase the surface potential above this, then only the inversion charge carrier will come into the surface, correct? So by using the previous QC equation, this equation, we can again derive the total channel charge, which is nothing but by ignoring the whole contribution, we can get this channel charge equation. And we also know we can simply calculate the inversion charge and the bulk charge by the total charge. So QC dash is equals to the inversion charge plus the bulk charge, correct? This inversion charge can be calculated as follows. So method number 1, you have a surface where the inversion charge, first of all you applied VGB in such a way that the surface potential attain a value where depletion is maximum, and then inversion charge will come into picture. When you increase VGB, what will happen? This inversion charge is increases, and let us consider this point is exactly ys, y surface, and below this point you have a point which is called as yc. So if I consider this as y axis and this as x axis, along the y, when I am moving from y surface or ys towards yc and deep in the body, what will happen? This potential decreases. As the potential decreases, ultimately the charge decreases. So what I can assume that in between this delta y height, all the inversion charges are there. So if I want to calculate the total inversion charge per unit area, I can simply do the integration between ys to yc of all the charges present into this delta y. So delta y, and consider the ny electrons are there, and I need to multiply with minus q. This method we have already discussed when we were discussing about two terminal MOS structure, where we said that this method which gives us a simplification value of qi dash, but this is not that easy because we need to solve the numerical integration. Why? Because I am not very sure what is the limit of yc, meaning till what extent my inversion charge is spreaded up. Instead of following this method 1, we simply said we should go for method number 2. In method number 2, we introduced two very good and important approximations. The first one was depletion approximation, and the second one was charge sheet approximation. In depletion approximation, we said that when you apply a gate voltage, then the depletion region comes into picture, and this depletion region is defined by a sharp boundary, and there is no mobile charge carriers present into the depletion region. This region is defined by dB depth, and the second is we assume that the inversion charge is made up of a very thin sheet near the surface and inversion layer is approaching to 0. So, all the surface potential will drop across the depletion region. Following method number 2, we extracted total bulk charge as minus 2 into Q into Na into epsilon s square root of psi s. If we know Qb dash, we can simply calculate Qi dash by using this equation, which says that the total channel charge is nothing but the inversion charge plus the bulk charge. So, by this we can simply write the inversion charge equation, which is nothing but minus 2q into epsilon s into Na square root of psi s plus e to the power of psi s minus 2 phi f plus Vcb. This point you should take care of, because in earlier two terminal MOS the equation was phi t e to the power of psi s minus 2 phi f over phi t. But here, as we have already discussed, the moment you inserted Vcb, ultimately surface potential should fight against 2 phi f plus Vcb. So, ultimately the attractiveness of the surface can be defined how much surface potential is greater than your Vcb. Following this, we can use some alternative expression for Qi also by using our well known potential balance equation. So, we know that Vgb is equals to V flat band voltage, or Vgb equals to phi ms plus psi s plus psi ox, where psi ox can be replaced by Qg bar Qg dash by Cox dash. Again, this Qg can be replaced in terms of minus Q naught dash minus Qc dash. By using all those terms, phi ms plus psi s minus Q naught dash by Cox dash minus Qc dash by Cox dash, you will get an equation for Qc dash, which is nothing but minus Cox dash into Vgb minus V flat band voltage minus psi s. So, this term plus this term is nothing but V flat band voltage. Again, if I am interested in inversion charge, I can rewrite this inversion charge as Qc dash minus the bulk charge, where Qc dash is the total channel charge, and hence you can get minus Cox dash, you take common and you will get Vgb minus V flat band voltage minus psi s minus gamma times of root psi s, where gamma is nothing but body effect coefficient. We have already discussed in detail about this. If you put back in this equation of Vgb, you will get a closed form equation of Vgb. Again, if you see here, the electron concentration at the surface is not only a function of Vgb. Instead, you can see that it is a function of Vcb also. So, the inversion charge which is present near the surface is not only controlled by Vgb now, it can be controlled by the external new terminal which is defined as C, and the Vcb voltage is actually controlling your inversion charge. Following the same equations, we can simply derive what is the capacitance in bulk and inversion. This is nothing but given by Cb dash is equals to minus of delta Qb dash divided by delta psi s, or change in bulk charge with respect to change in surface potential. Similarly, Qi dash can be defined as minus dqi divided by d psi s. So, using the equations of inversion charge and the bulk charge from previous slide, we can simply differentiate with respect to surface potential and get this closed form equation. Again, if you see carefully, in the depletion region capacitance also, there is a term psi V psi b is coming into picture. So, one might get confused that we have discussing that Vcb is not affecting the depletion region, whereas the Vcb term is coming into the capacitance. So, we will see later when we will plot the graph, because we are discussing that VCB is not affecting the depletion charge, but VCB will affect the change in depletion charge. There is a difference. That's what we have discussed when we were discussing about the small signal capacitance. The capacitance is not charge per voltage. The capacitance is the change in charge per change in voltage. So that is what VCB, which is coming here. This shows that the change in VCB reflects the change in depletion charge, but ultimately when you are in depletion, the VCB will not come into picture. We will discuss thoroughly in terms of surface potential versus VGB graph. So if you plot all those equations, all those crunching equations, whatever we derive for 2-terminal and 3-terminal MOS, ultimately you will ended up with these few important graph where we are actually plotting psi s, capacitance, log of Qi dash means inversion charge or inversion charge with respect to gate body voltage. Here there is another x-axis is given, which is VGC, which we are going to discuss in next lecture when we will discuss about body effect. So as of now you consider only this x-axis where we are talking about for a fixed VCB, what is the impact of VGB? Increasing VGB, the surface potential is increases, but because of presence of VCB, ultimately you need to fight against not 2 phi f, rather 2 phi f plus VCB. That is what these dotted lines shows the graph of 2-terminal structure. So if in 2-terminal structure, when VCB was not there, if the weak inversion or the strong inversion starts at this point, which is surface potential of 2 phi f, where we discussed that after this point the surface potential gets pinned, right. So this point is shifted to a new value of what? 2 phi f plus VCB, because you increased VCB, and hence you need to include, and hence you need to apply more amount of VGB to attain the same amount of surface potential, which causes the inversion. So this point is got shifted here. So this is the new point which can be said as onset of weak inversion. So this can be onset of weak inversion, this is onset of moderate inversion, and this can be considered as onset of strong inversion when VCB is coming into picture. So the impact of VCB is nothing but to shift everything to right in the sense it requires more VGB to attain the same amount of conduction or same amount of inversion charge. If we see closely about the capacitance graph, first thing is we remove the B terminal here. That's already I have discussed in previous lecture that we are actually plotting 1 over Cg dash, because now the body voltage is also associated with the contact C. So we are plotting Cg dash, not Cgb dash. The second thing is, when you see the capacitance voltage characteristic of a 2-terminal MOS, then what we found is it decreases from accumulation to flat band to depletion to weak inversion, and after weak inversion it suddenly rises up and approaches the Cox value. This dotted line is for 2-terminal MOS and for low frequency. We argued on the frequency that when you increase the frequency of the signal, the charge carrier will not get enough time to respond, and hence the capacitance will stays at minimum for high frequency. This is the case when the inversion charge is not connected with the external environment, because the inversion charge in 2-terminal MOS was only coming from the body due to generation and recombination. However, when you connected VCB, the inversion charge is connected with the external body. It means external contacts. So it means when you change VCB, the change in frequency can be responded by the change in charge, and hence this graph is for both low and high frequency. That is a significant change in 2-terminal and 3-terminal structure, because now the inversion charge is not only coming from the body, majorly it is supplied by the other terminal, which is called as C in this case. Now, but yes, if the frequency of the signal is very, very high, it might get stayed at the lower value. Let us discuss about the log of Qi dash. We also know that this log of Qi dash is very important to discuss about or to find out which region of operation you are. Meaning, in general, Qi dash is directly proportional to e to the power of applied gate voltage by eta or n into phi t in weak inversion. In general, Qi dash versus VGB graph is almost linear in strong inversion. So, this is the method to actually identify in which region of operation you are. You can see from here that we said that this rise in Qi dash is gradual, it is not abrupt. Because of exponentially dependency, it is gradual, and hence what we will do, we will take a tangent of it, this will give me extrapolated threshold voltage. So, this line which is dotted is shown for 2 terminal MOS. So, this was the threshold voltage which was defined as Vt naught, but here in terms of gate body voltage, we are defining a new term as Vtb. In earlier case also, we were having only gate to body voltage, but there was no C to body voltage or contact to body voltage. So, we have taken a notation of Vt naught, but now we have 2 voltages connected with reference to body. So, to make a differentiation, we are just introducing a new term Vtb. Vtb means this voltage is measured in respect to VGB. The same thing we can observe in weak inversion, meaning if you see this graph plotted between surface potential and VGB, let us consider we are plotting this graph for a fixed value of VGB. We termed it as VGB5. You can take anything, so we have just taken a random number VGB5. So, you have a 3 terminal structure like this, and here it is VCB and here it is VGB. Now, you fixed VGB to a particular value of VGB5 and you are varying VCB. Then what will happen? We have already understood this phenomena using band diagram, but let us understand qualitatively. You fixed VGB, let us consider you fixed VGB in such a way that, or let us understand like this, you fixed VCB first and you kept VGB so low in such a way that you are not in depletion even. So, when you fixed VCB, there will be a depletion region formed between N plus P junction because of fixed VCB. Now, what you are doing? You are increasing the VGB, and when you increase VGB, this surface potential rises up. Because of this surface potential, there will be a depletion region starts to form. There is a point at reach when the depletion region below the gate and below the N plus region almost become same. At that moment, the potential of the surface measured with respect to this point, either at this location, either at this location or at this location or at this location even, will almost same. It means if you further increase VGB, the electrons will be in favor of this surface, and hence the electrons will come like this. They form a depletion region. They form a depletion region because everywhere near the surface you make a voltage same by applying VGB and keeping VCB constant. But now what you are doing? Now you let's increase VCB. If you increase VCB, again you are increasing the positive potential at the N plus, and hence the electrons will see a favor towards the N plus, and hence the depletion increases and the inversion decreases. So, increase in VCB makes your inversion lighten, whereas increase in VGB causes higher inversion. So, you can see the impact of these two voltages are opposite. You can reframe this complete study as you have two voltages. When you increase VGB, the surface potential is increases. That surface potential causes more electrons to come here and the inversion layer forms. Now, when you increase VCB at this side, you are ultimately increasing the positive force or attraction force to those electrons which will go towards VCB, and hence the inversion layer will be decreases. There will be a point reached when VCB is so high that complete inversion charge will go back towards the VCB, and hence you will only left with depletion charge. That is what it is visible from this graph, which simply says that let us consider you have a fixed VGB now, which is VGB 5, and you are in strong inversion here. Now, what will happen when you increase VCB? As we just discussed, increasing VCB is attracting the electrons towards the N plus side, and hence you ended up with moderate inversion. So, the inversion is getting lightened. Now, you further increase VCB to VCB 3 value. Now, your moderate inversion enters into weak inversion. If you go on increasing VCB, you will left with even depletion. The interesting part here is, if you see beyond this particular value, the change in the surface potential is not visible, meaning the surface potential is not get affected by VCB value when you enter into the depletion or weak inversion. That value is given by dashed line, which is nothing but what? Psi SA. So, when you enter into the weak inversion or depletion, the impact of VCB is lost, and that is what we have already discussed in starting, that the VCB is only influencing your inversion charge, neither depletion nor accumulation, and significantly not in weak inversion. So, these are the equations for psi SA in depletion, in deep in depletion, and we will find that there is no term which is actually coming up in terms of VCB. However, we saw one interesting term that VCB will come surely in CB dash, because the change in VCB changes the depletion region charge. So, let me summarize. We have seen that when you introduce a third terminal in two terminal MOS, then this third terminal will govern or will capture the influence, the third terminal will influence the inversion charge. Thus, we can use all the models what we have derived for two terminal MOS for three terminal structure also, with replacement of N naught by N naught into e to the power of minus VCB divided by phi t, and the surface potential would be replaced by 2 phi f by 2 phi f plus VCB, which simply says that when you increase VCB at the C to B terminal, then you have to have a higher surface potential such that the same amount of inversion can be attained. So, we will stop here for today. Until then, take care.